Hi, today we're doing Fluent Project 2, which is a simulation of airflow over a plate. So we're going to go ahead and add a fluid flow with Fluent to get started. And name this Project 2. And then we're going to work with Design Modeler just to model our plate, and the dimensions are going to be 100 centimeters in length and 10 centimeters in height. So we're going to go ahead and change our settings here to have our grid so that everything's more precise and coherent whenever you're looking at it. Then we're going to add our rectangle in. And then add our dimensions. And then again, our height is 1 meter, and our height is 0.1 meter, and our length is 1 meter. So after that, we can go ahead and assign our sketch to generate a surface and apply that. And then we can generate, the filling and move on to the meshing process. So from here, we can go back to the z-axis and generate the mesh. And we see here that it's not really the resolution that we want. So we're gonna insert a face meshing and apply our mesh to that. And then we can insert a refinement, but instead of upping the resolution, we really want it to, ascend in resolution closer to where the wall is. So we're gonna start from the left side and add 40 divisions, or we're gonna just add 40 divisions on top by selecting the top and bottom sides like that. And then now we're going to work on the left side here and add 50 divisions. And our factor is 60. So after we generate that, then we can see, there's more resolution towards the bottom, which is what we want, but we have to make it symmetrical. So we're going to apply the same to the right side. And now this is our generated mesh, which looks good. It has the resolution where we want it. And we're gonna go ahead and name all of our sides and the face of our mesh. The top one is our far field pressure. The bottom is our plate. The left hand side is our inlet. The right side is our outlet. And then we're going to call our face the air. So just to verify, we can run through these and see that everything, is selected correctly. So we can close that out and update our mesh. And then work on our setup. Here we're just looking at our task manager to ensure that we have enough logical processors. So we're doing 1 less than 20 and double precision, and then we can start. So this is what our mesh looks like here. the vectors are pointing, the correct way. And let's change this to laminar flow. And then we're going to change the viscosity to 1.8 because that's just the number that we use to calculate our Reynolds number. So we want everything to match. In our inlet, we want to be 2 meters per second, our velocity magnitude, and our outlet should be the same. Our far field pressure inlet should be the same, but we're going to change our type of our plate wall, I think, to our far field pressure to symmetry, just to make the calculation simpler and ensure that everything else has the correct type. So our residuals should be 10 to the negative 7. And then we're good to start the initialization process. And we're just going with standard this time. And our compute form is, the inlet. Our iterations, we want to be a high number, but hopefully our solution converges, before it reaches that number. So we can go ahead and run our calculation and watch as, our lines descend, which is a good sign. And we can see here that, the error is decreasing and that our solution converged before the number of iterations ran out. So we can go ahead and take a look at our coefficients of drag. So we generated those. And here's a look at our contour, which we can open up our solution to, have better controls over that and add in our velocity vectors. So after this loads, we're going to go ahead and add a contour. And we can go ahead and see here that our pressure, is higher at the inlet and much less towards the outlet, which is what we should be seeing. And we can see like a little of that shearing against the bottom wall. So we can go ahead and add our velocity vectors. And we can see, there's a region closer to the wall which is entirely blue, and then up above it's red, which increases in magnitude. So we have that no slip condition against the wall, and then we have the higher intensity velocity vectors away from the wall towards the far region. And this is our profile, what it looks like. So we're going to insert our line so that we can go ahead and plot it on the graph and create actual velocity profiles. Here we're going to do the inline in 100 samples, so that faint yellow line. And then we're going to add in our X value at 75 centimeters and examine that. and then we're going to add in our 35 centimeter line. So here I'm just making the velocity profile for our 35 centimeter line. The recording stopped at the 75, but we're going to recreate that in Excel, and I'll insert that at the very end. So here's the curve. And then here's the 75 centimeter plot in Excel. This is data that's downloaded from the Fluent simulation and compiled and compared against the calculated theoretical.